In this video, we'll be looking at the three trigonometry ratios for right triangles. So the trig ratio compares the sides of right triangles in relation to an angle that we call theta. So theta is a Greek symbol that is used commonly with trigonometry, and you'll see that in this diagram it is drawn next to angle A of this right triangle. So what that means is that we have three sides that always show up when we deal with trig, and those are the hypotenuse, which we already know about, but then to identify the two legs, we are calling them either the opposite leg or the adjacent leg. And so it depends on where theta is. In this first picture, we have theta in angle A. The hypotenuse is always going to still be across from the right angle. So because this side AC is directly across from angle B, that is still the hypotenuse no matter what. But since we now have these two legs, we have to decide, well, which one's adjacent and which one's hypotenuse, and they're in relation to theta. So the side that is opposite from theta, or angle A, will be across from it over here, BC. That will be our opposite if that was our angle. And then the side that is next to it, or adjacent, remember that word just means next to, is this side AB because it's directly touching that symbol theta. So we have three ratios that come out of this. The first one is called sine, and the sine function tells us that if you take the sine of theta, then it will be the same as the opposite over the hypotenuse. So if you know those two side lengths, you can put them in a ratio and solve them in order to determine what the sine of that angle theta is. We abbreviate the word sine with SIN, and that's how you'll see it on a calculator. Then we have the cosine function. So cosine of theta using our triangle will be the adjacent over the hypotenuse. And again, if you know those two sides and you put them into a fraction simplified, that will be your ratio that represents the cosine of theta. Finally, then the tangent comes from doing the opposite over the adjacent. So you're just going to take those side lengths and put them into that ratio. Notice cosine was abbreviated as COS and tangent was abbreviated as TAN. You're taking these as a function, so it's not like sine is being multiplied by theta, it's saying the sine of theta, so you're putting it into the sine function. So the opposite and adjacent will depend on which angle is theta. If we had drawn it another way where we had triangle ABC again, and said that our theta was now at angle C. Well, our hypotenuse is still across from B, but now the opposite would have been this side, and the adjacent would have been over here. So it depends on which angle is theta. But theta will never be the right angle. It's going to be one of the two acute angles in a right triangle. One of the ways that we can remember these three ratios is the phrase SOHCAHTOA. So it's kind of catchy, SOHCAHTOA. Reminds you of the order. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So it's just a quick way to remember the order and which ones go with which function. So we're going to try to apply this given this right triangle. And in our first diagram, it says theta will equal the angle R. So I'm going to draw the theta symbol next to angle R to remind ourselves. And as soon as you do this, it's really helpful to label which one is adjacent and opposite and hypotenuse. So our hypotenuse is always across from the right angle. So in this case, it's 10. The side that is directly across from the angle theta is always your opposite. And one of the sides, or one of the legs that touches that angle is your adjacent. So now it's labeled, and we're going to complete our sine, cosine, and tangent of the angle R. So the sine of R, remember, so opposite over hypotenuse. Well, our opposite side length was 8, and our hypotenuse length was 10. We'll simplify this, and it becomes 4/5. The cosine of angle R is your ka, part of SOHCAHTOA, so that is your adjacent over hypotenuse. The adjacent side was worth 6, and the hypotenuse was worth 10. Simplified becomes 3/5. And then our last side, or our last function, tangent, our tangent of angle R is our opposite over adjacent. Remember, that's the TOA part of SOHCAHTOA. So our opposite side was worth 8, and our adjacent side was worth 6, so 8/6, which simplifies to 4/3. So now that we've done it for angle R, we could also have done all of these functions from the angle S. And these actually should all say sine of S, cosine of S, and tangent of S there. So we're going to be looking at where theta is in relation, or which sides are which based on where theta is as angle S. So our opposite now is across from theta, so that will be our side length of 6. The side that is adjacent is 8, and the hypotenuse stays the same because it's still across from the right angle. So sine is still opposite over hypotenuse. So our opposite side now is 6, and our hypotenuse is still 10. So this simplifies to 3/5. Then we have our adjacent over hypotenuse. Adjacent over hypotenuse here will be 8 over 10, which is 4/5. And then our opposite over adjacent for our tangent, so TOA in that SOHCAHTOA phrase, our opposite side was 6 and our adjacent side was 8, and that will simplify to 3/4. So notice how some of these were changed based on where theta was in the triangle. So we can also simplify them down to a decimal. So once you are actually given some of these sides, rather than just leaving it in a fraction, you can put them into the calculator and get a more accurate answer here. So as a reminder, sine is our opposite over hypotenuse, or SOHCAHTOA, so the SO part. And we're taking this from the angle A, so theta will go on A. Our hypotenuse is root 21 because it is across from angle B. Our opposite is the 2 root 3 side, and our adjacent is that one that is worth 3. So our opposite length was 2 root 3, and our hypotenuse length was root 21. Now, if we were going to ask to be leaving this in simplest radical form, we would need to rationalize this denominator, but since we want to just round it to the 4th decimal place, we're going to stick it in the calculator, and when we end up rounding that, we are left with this number as an approximation of what the sine of A would be based on this triangle. Cosine comes from doing your adjacent over hypotenuse, so we put our adjacent side of 3 over our hypotenuse of the square root of 21. Again, put it into your calculator and you are left with this precise amount here. And finally, we have our opposite over adjacent. The opposite side is 2 root 3 and our adjacent side is 3. In the calculator, that comes out to be 1.1547 when we round to the 4th decimal place, or the nearest 10,000th. It is important, though, when you are going to now solve some of these in your calculator, that you are checking that your calculator is in degree mode. This is probably something that you haven't even ever played with on your calculator. There are 2 modes, radians and degrees. For now, we are only focusing on degrees. Since we know degree measures of triangles, we're focusing on it in terms of degrees right now. So we're going to actually plug these into a calculator. So you can use the Desmos Virginia testing calculator, and it should default to degrees. And you'll just type it in as sine, S-I-N, in parentheses 26, and close the parentheses, and that should give you a value. Now we're asking you to round to the nearest 10,000th place, so 4 decimal spaces. In the calculator, you will see 0.43837 and so on. I'm writing that 5th number down so that we can check it and see if it needs to round. I want to stop where the 3 is, but because 7 is there, that's going to round that 3 up. So the rounded answer for this will be 4384 after that decimal point. Same thing with cosine of 35 degrees. We're just going to type in COS parentheses 35 and close the parentheses, and you end up with this amount. Again, I'm writing the 5th number so that we can look and see what will happen to our 4th decimal place, since there is a 5 that rounds up the 1, and so this would turn into 8192 after the decimal. Tangent of 47, you type in tan, T-A-N, parentheses 47, and then you would write 1.0236 and so on. It comes out. So we do need to end up rounding this because of that 6. It will bump the 3 into a 4. So these are our four places after the decimal rounded to there. Always look at the 5th place to decide how you're going to round to the 4th place. Finally, we're going to do two application problems here. We want to find the missing sides of the right triangle, and we'll do the same thing with this word problem down below. So notice how you have this right triangle given to you. Right away, what you want to do is label your hypotenuse, and then look at where your angle is. So the only angle we're given here is 40, so I'm going to treat that as theta. You could find 50 down here and use that as theta as well, but if there's already one given to you, you might as well just use it. Because that's our theta, 8 is our adjacent side and y is our opposite side. So I need to find x and then I need to find y. So since I'm going to use x, I'm going to decide that I will be using my hypotenuse and then the side that I do know a value of, which is your 8. So adjacent and hypotenuse. Well, the one that uses that is the part of SOHCAHTOA, so we're going to use cosine here. Cosine of theta is the same as adjacent over hypotenuse, and then we'll plug in what we know. The theta is our angle, so when you know it, you need to plug it in. We're going to say cosine of 40 equals your adjacent, which is 8, and your hypotenuse, which is x. And we just need to solve this for x. Well, to get x alone, we kind of have a few steps to get through. In order to make the x no longer be in the fraction here, we're going to multiply by x on each side. When we do that, it's like x over 1, so x over x simplifies to just 8 over 1, which is 8. Then on the other side then, we have x times cosine of 40. Well, to get x alone, we would just have to divide by the cosine of 40. So we can put all of this right into our calculator as 8 divided by the cosine of 40 to get an approximation for x. And when we do that, and we round to the nearest hundredths place, because this says round to 2 decimal places, we end up with 10 and 44 hundredths. So not finding cosine at the beginning there and not pre-rounding, make sure that your final answer is accurate. So don't type in cosine of 40 up above and get a decimal and round mid-problem, otherwise it will affect your final answer. And then our second part we need to find, now that we found x was about 10.44, we need to find y, and y was our opposite. Now, we did just find the hypotenuse, but I would suggest using that whole number that wasn't rounded to be very precise in finding y, which means we're going to be using our adjacent and our opposite. So the one that uses those two sides is your tangent function. Remember, TOA for tangent of theta is equal to opposite over adjacent. Again, our theta is our angle measure, so we said it was 40 degrees. So tangent of 40 equals your opposite y over your adjacent, which was worth 8. So in order to get y by itself, we're going to multiply both sides by 8. Remember, this is like 8 over 1, so it's allowing those 8s to simplify to 1, and we're just left with our y value. And so to get that, we just have to type in 8 times the tangent of 40, and we should get 6 and 71 hundredths, and that would be our side length there. So once you've solved this triangle, make sure that it makes sense. 8 and 6.71 are both smaller than their hypotenuse of 10.44, so that means it's realistic. You could even take it a step further and check it with Pythagorean theorem if you needed to find that and verify that you had solved it correctly. Finally, we have a problem that says a hill frequently used for sledding has an angle of elevation at 30 degrees at the bottom. If the length of a sled ride is 52 6/10 of a foot, estimate the height of the hill. So we're going to draw a picture, and I'm just going to make it look like our previous triangle. And this will be the hill that someone is sledding down, and they said that it would be a sleigh ride of 52.6 feet. The other thing that we know is that it has an angle of elevation at the bottom. So that means that this angle down here is going to be worth 30. If it had said an angle of depression, we'll talk about that. That would be below that amount. So we'll get into that in a couple lessons from today. So at this point, they're saying estimate the height of the hill. Well, the height of the hill would be this side over here, or in terms of our trig ratios, our opposite. And the side length that we know is our hypotenuse. So since we know our opposite and our hypotenuse, that's going to be us using the sine function for so. So we have our sine of theta is equal to your opposite over hypotenuse. And then we plug in what we know. Theta is 30 degrees here. Our opposite side is what we're trying to solve, so we can call it x. and our hypotenuse is 52 6/10. In order to solve for x, we're multiplying by 52.6 over 1. On this side, 52.6. So these two 52.6's cancel each other out into 1, and we're just left with our x. We multiply 52 6/10 times the sine of 30 degrees, and we are left with 26.3. And since it was talking about a problem that we're trying to solve here, it would be that many feet. And that seems reasonable because it is less than our hypotenuse in that triangle, so we know that that would be allowed.